All right, I will go ahead and get started. So I wanted to begin by reconciling something that was brought up towards the end of actually it was during question time. We were talking about radii and factors of 2 in experimental definitions of radii and so forth. I wanted to try and explain that a little bit further. And then we'll talk briefly about another electromagnetic process, and then we'll move on to talking about systems with P-wave interactions. All right, so this is the formula that I spent maybe all of my second lecture yesterday deriving, and it says that the square of the electromagnetic radius for the deuteron goes like, well, it doesn't go like, is equal to this factor which comes from the wave function renormalization, but is not interpolating field dependent, times the leading order result, which is 1/8 gamma squared. And gamma here is the square root of m times the binding energy, or more generally, the square root of twice the reduced mass times the energy needed to remove 1 neutron. So this is a symbol I'm going to introduce today so I can talk about weakly bound systems in nuclear physics other than just the deuteron. The nuclear physicists call this the 1 neutron separation energy, and it means exactly what it says on the tin. It's the energy it takes to remove 1 neutron from the system. All right, so I'm going to claim without proof, but maybe we can do it as an exercise, that if you generalize this result to the case of unequal masses, in other words, to the case of a weakly bound state between a core and a neutron, rather than the weakly bound state of the proton and a neutron, then you get this formula where F is 1 divided by the mass number of the core plus 1. So for the proton, A sub C is 1. But for beryllium-11, A sub C is 10. And immediately, you're going to ask yourself the following, hopefully you're going to ask yourself the following interesting question. Suppose I have a neutron halo, like beryllium-11. I don't know if you remember my picture from the first lecture, but this is a neutron halo, like beryllium-11. And you're going to ask me how, if I come in with a photon, am I able to measure an electromagnetic radius, which is related to the size of the halo? So the answer is actually intimately tied up in this factor of F. This is you could think about this as a center of mass effect. So the center of mass of this system is not the center of charge. The center of charge is here, the center of mass is here. And this distance means that there is a non-zero electromagnetic radius associated with the photon coupling to the core. But because it's a center of mass effect, this radius goes like 1 over this AC plus 1 squared, or the radius goes like 1 over AC plus 1, radius squared goes like 1 over AC plus 1 squared. So this is a so for the deuteron, this is the radius up to nucleon structure correction. So maybe for the deuteron, the picture looks more like this, right? But 2 things happen in halo nuclei that mean that this effect is, while important, is less critical contribution to the electromagnetic radius. And the first one is that this effect is suppressed by the mass of the core being large. And the second one is that these cores that are not the proton are bigger than the proton. And so the finite size of the core, which in the effective field theory enters as a counter term, it's going to enter as an operator with 2 derivatives that gives a finite contribution to the electromagnetic coupling. It's not that we neglect this effect where where the radius of the core comes in, it's just that we include it as a 2 derivative operator. So in this counting, it turns out to be N3LO. Fine, right? But both of those effects are more substantial for halos beyond the deuteron. All right, so coming back to this, so if we don't want to mess with that problem, what we can do is convert this radius into a distance between the core and the neutron. So we could have calculated that radius in the theory. I didn't do that yesterday because I wanted to show you how to couple electromagnetism and talk about charge conservation and so on and so forth. But if you do the calculation of the neutron core separation, you get this result. So for the deuteron, it's just 4 times difference in the square, and this is the factor of 2 that I was talking about dividing and multiplying by in the experimental results. So as was pointed out to me by, I don't know the name of the student who pointed it out to me, but it was a good point. The experimental result for the deuteron electromagnetic radius is half of this number. Half of this number. But you can convert the experimental number, because the experimental number for the charge radius differs just by this factor of f, so you can convert for the deuteron this number into a number for the core neutron distance, and you get this, which is in remarkable agreement with what we calculated for the core neutron radius. And then if you do the same thing, compute the core neutron distance using the EFT for beryllium-11, you get like a number of about 6.9 Fermis, which is big, right? It's a big number. And the experiment suggests something somewhat smaller. So maybe this difference is made up by higher order corrections. And then for carbon-19, which is also a halo, then the prediction is in excellent agreement with the experimentally measured neutron distribution. Down the bottom, I've put the S1Ns of all of these systems. So these last 2 are bound by 500 or 600 kV. And the reason I did that was just to show you that all of them are bound by substantially less than 8 MeV per nucleon. So they are all systems for which this description of a halo should be a useful way to think about the system. Yes. Yeah. Yes, right.
When you are doing with a core and a, what is the?
Okay. Yeah. So that, I mean, so the EFT for so-called halo EFT is really it's very similar to the pionless EFT, but as you point out, technically it has different degrees of freedom. But if I'm going to write down the Lagrangian for halo EFT, it's going to look, you're going to find it looks very similar. Let's do the leading order Lagrangian, right? And that's, sorry. Yeah, I need a kinetic term for the dimer. Or a kinetic term of free power. Okay, and that's it. Right, so it's the same, I mean, so people will tell you, even I could, I mean, it's a fair statement, right? Halo EFT is a different effective field theory. And in the sense that it has different degrees of freedom, that is true. But conceptually, it's the same.
There's an internal size of C itself.
Not at leading order. Right, so this is exactly what I was saying, right? So thank you for giving me an excuse to say more about that. So at leading order, the core is treated as point-like, which some nuclear physicists will tell you is crazy. But then you correct for this at higher order. So for instance, if you want to, I'm going to try and do this on the fly, right? But if you want to include the finite size of the core, you're going to include, I'm not sure I'm going to be able to write down a gauge invariant operator on the fly, but you're going to include some operator that looks like this, which, and this is obviously not gauge invariant, but by being suitably careful, I can make it gauge invariant. And this operator is going to generate a coupling of the A0 photons to the core, which goes like Q squared. So this operator comes with 2 derivatives. So the counting here is that this operator would be order Q squared, and leading order is 1 over Q. So this is an N3 LO effect. Okay. And the deuteron, that works pretty well, because the basically because the center of mass issue doesn't produce large factors in any place, and the proton it really is small compared to the entire system. Okay. Yes. So this is, I should say, this is the next leading order result. So you have to think a little bit about the expansion parameter here. So this, unfortunately, I ran out of, if I put the, let's see, can I fit this on? I'll put it over the top, right? So if you have, for each of these, you have some information on the range of the interaction. And so you can write down what you expect the expansion parameter to be. This is related to what I was saying to Tuhin about the proton being sort of smaller. So here the expansion parameter is about 1/3. This is just based on looking at the range, basically the ratio R over A. So the range of the interaction divided by the scattering length. For beryllium 11, it's 0.4. And for carbon 19, it's 0.6. Now, this is an NLO result. So a priori, I would say that this one would have a 16% error, this one would have like a 40% error, and this one would have a 10% error. So I don't actually think that this one is terrible. It's within about 20%. It's not that. I think these two are remarkable, right? I don't understand why it works that well for those two systems. I would also say that this is only one of 2 experimental numbers. I picked the one that was more precise. I didn't pick the one I liked. But the other experimental number here disagrees by more, because it's difficult to measure a neutron distribution. There's a lot of uncertainty when you try and pull that out of the data. Okay, so you can really, the clean one is deuterium, because you can get this proton-neutron distance directly from the electromagnetic radius once you correct for proton finite size, which you know what that is, right? So, yeah. All right, does that answer your question? Yep. You see, it's always, right, I think EFT, it's very interesting, right? So EFT people, after you see a couple of EFT things that work to 1%, and you see something that only works to 10%, you say, well, clearly it's failing, right? But maybe 10% is the expected accuracy. So I think it's very important to think about what the expected accuracy of the NLO prediction actually is. All right. So that was all I wanted to talk a little bit about charge radii and I guess also neutron radii here. Let me talk about photodissociation. So, okay, so I'm going to do this. We're going to do electromagnetic breakup of the halo. But if you don't like halos, if you prefer deuterons, you can just replace the C by a P, and we're doing electromagnetic dissociation of the deuteron. So the Feynman rule here comes, so what we're going to think about here is not the magnetic piece that Professor Kaplan was talking about, but the so-called E1 breakup due to electric coupling. So the electric coupling comes from the minimal substitution to the charged core. So I'm going to take to representing cores by dashed lines and neutrons by solid lines. And so when I do minimal substitution, including the charge of the core, I get a Feynman rule like that. And when you sit there and stare at this for a minute, you'll realize that this is just the photon, that this just says that the photon couples to the classical current, which is the charge of the core times its velocity. So then the single Feynman diagram for this process at leading order is this. This is a pretty easy calculation. And I times, I'm going to start using M because now I'm calculating a different process, is minus IGI divided by, so we have this propagator here. You have a question? This, oh, sorry, this is the photon. So this is like, so this is the photon polarization vector. Yeah. Thanks, yep, I didn't say that. So this photon is a real photon when we do, it's coming in an external state, so it has to obey K0 equals absolute value of K. It has some polarization vector epsilon. And as we were just discussing, we're going to have to do this for two different polarizations. If you're a sophisticated experimentalist, you can measure this with right circularly polarized photons and left circularly polarized photons and take the difference. This is actually how you can separate the M1 and E1 contribution to this reaction because they transform differently under what is that, time reversal, I guess. Right, and now I'm trying to be careful. We'll see, actually, I'm going to call this S1N, just for fun. I'm trying to be careful because now I'm going to work in the center of mass frame of the incoming halo nucleus, which is not the center of mass frame of the system because I also have the photon. And then going out, we have some momentum P plus K, and this one is minus P. So I'm not going, so this propagator here is the same sort of propagator we saw yesterday when computing the form factor, and that's not surprising. And this crops up all the time in these halo EFT calculations. This is just going to, this is, as I said yesterday, up to an overall factor. This is the momentum space wave function of the system. So if we go ahead and renormalize this, we have to multiply this time by the square root of the wave function renormalization because we only have one external Geimer field. So we have G square root D. We have 2mr, this is a 2, not a Z, divided by gamma squared plus P squared. We have E, we have epsilon I dot P, and we have an M in the denominator. And I claim that when this is done and you put in the square root of ZD, you get E times the square root of 4 pi times the square root of 2 gamma. In other words, you cancel the G, which is good because the G is a scheme-dependent quantity and shouldn't appear in the final result. Yes, thank you. And I should make this mod E to be, if I'm being careful. Yeah, on my sheet, I did it for the deuteron. And then I'm trying to map as I go, which is always a dangerous exercise. All right, and so what is this? This is actually can be interpreted as mod E times the leading order wave function times epsilon I dot P times the factor Tuhin pointed out of ZC. Because the leading order wave function, actually it's divided by 4 pi. Oh, sorry, times by 4 pi. Because the leading order wave function is a spherical harmonic, 1 over root 4 pi times this thing, which gives me a properly normalized wave function. If you don't like quantum mechanics, you can just not write this last line down. But if you like quantum mechanics, you can think about what you've derived that way. If you don't like quantum mechanics, oh, sorry, yes. Oh, sorry, yeah. So this is meant to this is the propagator. So this vertical line is this, gives you this propagator, right? So the vertex gives you minus IG. The vertical, it's really this propagator here, because this one is in the final state and gets amputated. If you work out this propagator, it gives you this result, and then this is the electromagnetic vertex. So I will tell you why I write, because there's if minus S1n was actually a positive quantity, there would be a cut. So that's why I think about it as a vertical line. Right? It indicates the presence of an NC cut associated with that state. Okay. And if you don't like quantum mechanics, you can go directly from the amplitude to the, let me see if I remembered my, I will tell you. So what I'm saying here is that you just use the normal rules you would use in quantum field theory. You're going to square the amplitude. You're going to multiply by the outgoing phase space, and then you're going to impose energy conservation, and you're going to sum over photon polarizations and divide by 2, because you're really averaging over incoming photon polarizations. So Rupak computed this contribution to gamma d goes to NP. He also computed the magnetic contribution, put them together, squared them, and computed the cross-section, and then, as Professor Kaplan said, reproduced data. It's actually better than that. If you use this formalism to compute the cross-section for photon dissociation of halo nuclei, including the 3 over there, the deuteron, beryllium-11, carbon-19, you can, when you do the calculation this way, you can see all the nucleus-dependent factors, the neutron separation energies, the masses, and you can then put all the data on the same plot, and you have like a single universal curve, and it actually describes the data very well. The universal curve looks something like this, and the data is, for the deuteron, the data is right on it. And then for beryllium-11, I think it's a little bit low, which is actually due to final state interactions. And from carbon-19, the error bars are bigger, but it works nicely. So anyone's interested, I have this plot in our review article, which I think the review article was circulated, so you can, but I'm happy to show it to anyone afterwards. All right, are there any questions? Yes?
So, when David calculates the term between sort of an HQVT expansion comes as sigma mu d FP. And that's the reason you're calling it a magnetic.
Yes, exactly.
And here it's like a grad of P dot P kind of.
Yeah, so here I would, again, at the risk of doing, you're going to do something like, in this case, there are going to be 2, right? Kappa core, sigma dot B, and then there'll be another one for the neutron. Actually, it's not kappa, it's mu, because it's the full magnetic moment, sigma dot B n. Oh, no, I'm saying if I wanted, yes, absolutely. So for this, sorry?
D dot P, right? I mean,
I think so D, where D is the dipole operator.
the
Oh, D, that, yeah, that's right. This is, so that's, but it's not D dot P, it's D dot, like it's, no.
D dot A.
D dot A, yes, yeah, yes, that's right. D dot A, right. So if I wanted to do magnetic interaction, I can do magnetic interactions in this theory. This is what, I think this is what you were saying, right? I just have to write down higher order operators, right? So the higher, because as we were discussing over coffee, right, the magnetic field involves an additional derivative, right? So this is curl of A. So this involves an additional derivative as compared to the stuff that comes in the leading order Lagrangian. So that's an interesting point, right? So this object is fully dressed, right? So I'm only calculating at tree level. You might think I'm only calculating at tree level, but I have all the non-perturbative interactions of the deuteron as it comes in. So yeah, I think David drew it this way. He put like the interpolating field here. So you create it and it doesn't go straight to the place it meets the photon. It does all its strong interactions before it gets there. Right, so this factor of square root ZD is critical because it gives you the dressed deuteron. You don't want the bare deuteron because you can't measure that thing, right? So you only because it's non-perturbative, you only ever see the dressed deuteron. Yeah, no, it's a good question. Yeah, because I admit, yeah. All right, other questions? Yes. Yes. The photon couples only to C because like at leading order, right? So the neutron will have couplings associated with its magnetic moment. It will have a two derivative coupling associated with its charge radius. And at some order, yeah, and right, yeah. If you could have two photon couplings associated with its polarizability, blah, 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 right? But at leading order, yes, it only couples to the core. Yes, D has migrated from meaning deuteron to meaning dimer, right? And here that's gonna, for the rest of today and tomorrow, that's gonna be a bound state of a neutron and an arbitrary charged core, which if that bothers you, you just make it a proton and you set S1n to B and AC to 1 and MR to big M over 2. That's a good, you can do that on the fly while you're writing your notes, and that'll keep you alert. You didn't, okay, nobody thought that was funny. I thought that was funny. Okay. As I tell my classes regularly, at least I amuse myself, right? If you can't amuse yourself, what's the point, right? So, all right. Other questions? All right. So this discussion of halos sets the stage for talking about P waves, because in nuclear physics, we don't just have shallow S wave bound states, we have shallow P wave bound states. So a couple of examples, that's over there, that state that I'm talking about is the ground, for beryllium-11 is the ground state of beryllium-11. Beryllium-11 is kind of remarkable in that it has a shallow S wave state bound by about 500 keV, and then it has an even shallower P wave state bound by 180 keV. So this is, we call this a 1/2 minus, because the bound state involves a 0+ beryllium-10 core and a neutron, but they're bound in a P wave, so the parity is minus. And S1n of this thing is 180 keV. But we can't we can't use that theory to describe this state because its parity is negative, so there's clearly some P wave somewhere in the system. So another motivating example is the helium-4 neutron phase shift at low energies. So, all right, let's do a little basic nuclear physics. So I start off, I have, proton and neutron, and they bind to form a deuteron, S-wave state, right? Then I bind another neutron, let's say, and I form tritium. So that's a proton and 2 neutrons. So neutron, proton, deuteron. Then we have tritium and helium-3. I'll talk about these when we do the 3-body problem later today and or tomorrow. And then I have helium-4. like this. All of these are S-wave states. But then I go to the 5-body system. Can I make an S-wave out of 3 neutrons and a proton? 2 protons. Actually, 3 neutrons and 1 proton also works. There are 2 possible answers, yes or no. The question is, can I make this state and have let's say everything be in a relative S wave? No, good. So why not? It will highlight, very good, it will highlight the Pauli exclusion principle. So the key thing about the reason that we are here is that nucleons are fermions, right? Otherwise, this 208 body system would collapse to something much more tightly bound than the lead-208 nucleus, because there would be bosons and they would just like that, right? It's a scientific term, right? So, all right, so crudely speaking, if I look at like helium-4, they have to arrange themselves like that if they want to be in an S wave. There are small, higher partial wave components to helium-4, but predominantly it's an S wave state. Once you go here, this is another motivating reason to think about P-wave halos, right? This is like, and so I can't, so if I want this thing, I have to put it in some P-wave relative to helium-4, or I have to put it far enough out that it doesn't Pauli exclusion principle with the others. In other words, so the shell model picture would be it can't be in the same orbital. Right? I would just say, so there are, it is possible to put a neutron in an S wave relative to helium-4, but it's not going to bind because it has to be out here, where it's not going to feel the Pauli exclusion principle effect. But if I look at the P-wave phase shift, in particular, what is this? I think it's the doublet P3 halves. So this is the neutron and the proton are in the neutron and the alpha particle are in a P wave with total angular momentum 3 halves. It goes up and actually passes through 90 degrees at very low energy. This is like, I'll check and let you know in the afternoon. It's like of order 1 MeV or less. So this is a low energy resonance. It's not a bound state, but it is going to be represented by a pole in the scattering amplitude, and it's going to be a low energy pole. And as such, it's going to be amenable to description by effective field theory. So with this as motivation, let's talk about P waves. Let me start with a few observations. So probably by now you got sick and tired of seeing this formula. Okay, because we're not going to see this formula much anymore because this is for S waves. I'm going to rewrite this as and then claim without proof that this generalizes to this when you want to look at a higher partial wave. So in fact, what you do technically is you start with the scattering amplitude as a function of K and theta, and you do a Legendre expansion on it. And this is just the ELF contribution to the Legendre expansion. So what does that mean specifically for P waves? Cosine theta 3, so I'll just absorb the 3 here, we'll put a 6 pi there. And then we have, and then I'm going to do, and then I have K divided by K, sorry, not K, I have 1 divided by K cotangent delta minus IK. Now, what want to think about the scattering as a function of angle. I want to think about it as a function of vector momenta. And so I'm going to rewrite this as, if I want to use vector momenta here, these both have length k, because this is elastic scattering, so the length of k prime is equal to the length of k. And so I get this form for the scattering amplitude. So a couple of differences from S waves. The first difference is, yes, that there's an angle upstairs. That's because it's a P wave amplitude. And the second difference, which is going to be very important for what we do, is that the quantity that has a analytic expansion around k equals 0 is actually this effective range function thing. I'll call this delta 1. This effective range function thing is k cubed cotangent delta. So the language here gets a little bit tricky. So let's do the following exercise. What are the dimensions of this thing, k cubed cotangent delta? K, what's k? Momentum, right? So yes, this is momentum to the power 3. So then what are the dimensions of A1? No, because it has to match this. So if this is momentum to the power 3, A1 has to be momentum to the minus 3, right? So A1, so if A1, most regular people call momentum to the minus 3 length cubed. If you went to the hardware store and you asked for a fridge of volume, I can't do it in my head, 10 to the 30 angstroms cubed, inverse angstroms, inverse cubed or something, you'd be laughed out of the store. But yeah, so it's length cubed. This is a scattering volume. And the dimensions of R1, what are the dimensions of R1? That one's momentum, right? And this, yeah, we take the trouble to change our terminology for A1, but we don't take for R1. We still call it the effective range, even though it's actually a momentum now. Okay. But I try to put it in scare quotes. The total amplitude is, yes. So this I was doing this heuristically, which is a teacher's word for wrong, right? So I was telling you, like, if you do this carefully, you start with f of k comma theta and you Legendre expand it. I'm just doing the motivation, right? So I said, here's the S wave one, it generalizes to this. So if I pick out the P wave component, it looks like this. In the differential cross section, yes, not in the total cross section, right? Yep. Well, we tend to analyze because bound states and resonances tend to occur with a particular J. We tend to do this EFT treatment of the strong part of the interactions in a particular partial wave. Right. One or maybe two, like in beryllium 11, right? But it's like a finite number where there are strong interactions, right? If all the partial waves had strong interactions, that would be a really hard problem. So, you mean like a priori? Yeah, so the way I tend to approach this is that I will assume that everything is natural until I have evidence otherwise. So that would mean all partial waves are weak except for the ones that are strong. So all partial waves are weak except for the ones that have low-lying bound states or resonances. So that's an assumption, but yeah. All right, so we're going to need operators with derivatives to describe P waves. We're going to need operators with derivatives because if we just write down operators that don't have any derivatives, they only probe the field at 0 separation. And at 0 separation, what is the amplitude of a P wave? I'll let you think about that while I finish cleaning the board. Let's suppose I'm in 3 dimensions. I guess I am in 3 dimensions. So if this is the wave function for an S wave, what does it go to as R goes to 0 if I'm in 3 dimensions? This is the 3-dimensional wave function, not U, right? Something like this, okay? So what does this thing go to as R goes to 0 if it's an S wave? Some non-zero number, right? So that's why we've been able to write down things like and not get 0, right? The bound state might do something like this. Okay, what about for P waves? 0, so because in general, the boundary condition on this thing for a partial wave L is that this goes like R to the L. Right, that's for the regular solution, that's the boundary condition. And this is associated with the fact that for the potential, you now have a centrifugal barrier, which is forcing you to have different solutions to the free Schrodinger equation. All right, so to get around this, so operator for P waves. So if I was being fancy, I would say that I have to point split the fields. So I don't know if that helps anybody, but that's one way to think about what we're doing. We're going to use the derivative to point split the fields. You could think about this as one, if I took the fields, moved them apart, and then Taylor sort of did a, what's that called, an operator product expansion type thing on the fields, then I would do something like this. Sorry, this should be psi diagonal, this should be psi. This derivative thing is the generalization to arbitrary masses of the one we have been using. You know, really, it's just a fancy way to get the relative momentum between the two particles. To do this, I had to invent something I'm very proud of, which is the M operator. If the M operator acts to the right, you get the mass of the thing on the right, and if the M operator acts to the left, you get the thing on the left. Actually, I guess let me make these, at the risk of messing up your notes, I'll make them N's and C's. Sorry, Tuhin. He just written down very neatly. Okay. So then the contact interaction here would look, it's pretty simple. Like that. And if I got my factors of 2 correct, then this produces a potential, or maybe I won't do it, I won't say that. It produces an amplitude at tree level that's just minus IC1 times K prime dot K. Where this is, let's say this is, now this is a C1. So this is a P wave separable potential for those of you who enjoy separable potentials. All right, so this is, I'm not going to do this, but maybe we'll do it as an exercise later. We'll see how time goes. I think this, I think it's a badly erased something here. Oh, sorry, yeah, I slipped back. It was psi, just a badly written psi. I was just putting a number out the front here of this one, of the same operator I wrote down. Yeah, so this, yeah, so I should be clear, right? So if I want to, so this over 2, this was for the old derivative operator where, so this, if these two have equal mass, I can use the old derivative operator we had and just divide it by 2 because that's the same as this operator in the case that the masses are equal. But if I want to generalize to unequal masses, which is what I've done down here, then I need these M operators to make sure I get the relative momenta. This fact, by the way, was missed in the first paper written on this subject. And so technically the operator that was written down was not Galilean invariant. But they got lots of other things right. All right. So now if we start, I want to just highlight a problem before we introduce dimers. So let's suppose we start trying to calculate loops like this. At this vertex, we'll get k prime dot p. At this vertex, we'll get p dot k, where p is my loop momenta. And this loop is going to be more divergent than the loops we had for S waves. I'll say that again, right? So here we have a momentum of the loop coming from this p wave vertex. Here we have a momentum of the loop coming from this p wave vertex. This loop is already divergent for S waves. It's integral d3p 1 over e plus minus p squared over 2mr. Now it's even more divergent. So this should already alert you that something interesting is going to happen in terms of the renormalization of this theory. The fun fact here is that that extra divergence is actually exactly related to the fact that you have 2 parameters that have, how do I say this, that 1 over A1 and R1 both have positive mass dimension for P waves. Because it turns out that those are exactly the things that you need to renormalize this divergence. All right, so did I already erased the dimer, right? Okay, so yesterday I got asked if I was going to write down a dimer for P waves. So here's a dimer for P waves. It's a vector because it has 3 components because it's a P wave. Other than that, this is exactly the same as before. Well, not quite, because the vertex is different too. The free part for the neutrons is the same. The free part for the core is the same. And then the different part is here. So here I'm just using this relative momentum operator to give me a vertex. Okay, so here, interesting question. So the dimer propagates in the center of mass frame of the total system, right? So the dynamics of the dimer is associated with the total mass. The relative dynamics of the neutron and the core inside the frame in which the dimer is at rest is associated with the relative momentum. It's, how do I put it? It's a good question because, yeah, it's very easy to get confused. Yeah. Yeah. Yeah, this is right. So this is here to make this, yeah, this is going to give you E minus the total momentum squared divided by 2 times the total mass. So it's going to give you the Galilean invariant energy of the 2-body system.
Difference coordinates.
No, for the, unless I made a mistake, right, when I wrote down the propagator for the dimer. But I have always, and I'm going to again, I've always computed the dimer in its center of mass frame. Right, so then you never see this term in anything that I've actually calculated. Okay, so speaking of, most of these Feynman rules you already have, so I'm not going to repeat them because it's almost lunchtime. So the Feynman rule for the dimer in an arbitrary frame looks like that. And if you do it in the center of mass frame, you just don't see this second contribution. And then here we have an object with polarization index I, let's say. Maybe I'll make it J so we don't get confused with the imaginary number. And this is minus I times G pi times MC Pn minus Mn Pc over Mn plus MC, and it's whatever component we're interested in the dimer being. All right, so in my remaining 4 minutes, we're going to calculate the self-energy of this thing. And then after lunch, I'll come back and we'll do some observations about what's happened. All right, so let's draw a diagram. So we'll start off with a dimer in its center of mass frame. It's going to stay in its center of mass frame, and we will start with component I and go to component J. So in principle, we're going to compute a matrix, sigma ij. But in fact, well, you'll see. So then if okay, so I will just say, so minus I times this matrix is minus I G pi squared for each vertex. I'm going to do an integral in big D space dimensions. I have the momentum associated with this vertex. I have the propagator of the two-body state, which, because we're in the center of mass frame, is just, this is the relative moment. So this is what you were saying, right? Is that you only ever see in the loop, you've only, if I was doing this calculation in an arbitrary frame, I would have to put, I'd have to put this here. But that's fine because it just basically it just changes what the integral is a function of. Okay, and then Pj. So if you deal with the factors of I, you discover that you're doing some integral, which may be familiar to you from other field theories where you have like a Pj, Pi thing upstairs. So you probably know that if you integrate this over the angles, you're going to get a delta ij. So if you do this in big D dimensions, you get delta ij divided by d. Big D space dimensions. And then what you're left with under here is p squared over E plus minus p squared over 2mr. And now we're going to exploit the fact, once again, that we're doing this in dimensional regularization. So if we add and subtract, (2mr) times E, this first piece gives us the integral of 1. And as we discussed during the exercises on Monday, that integral is 0. So it's actually the integral of -1, but it's still 0. Isn't that great? You can make a minus sign mistake and you still get the same answer because it's 0. So, and then you get 2mr times E times our favorite integral, Yes. Okay, so I guess I should have put plus I epsilons here. Okay, so now today I'm going to do, since Dr. Kaplan told you about PDS yesterday, I'm going to do this integral in PDS. I'm going to find that sigma ij is in the center of mass frame is delta ij times minus mr g pi, actually g pi squared. I'm going to keep going with the eraser. Two mre divided by 2 pi times 1/3. This is just the 1 over d in 3 dimensions. Ik plus 3 over 2 times mu PDS. Just for fun, I'm going to say this. If you care, great. If you don't, forget it. The fact that this is 3 halves has to do with the fact that if you strictly implement PDS, you subtract the pole in 2 dimensions. And in 2 dimensions, this factor has a 1 over 2, not a 1 over 3. But this doesn't matter in the end, because as Dr. Kaplan keeps emphasizing, it's just a scheme and you're free to choose a different scheme if you don't like that one. So as they say, I'm circling the plane. We're about to land. But I want to spend 2 minutes to talk about what's happened here. So first, the good news. Actually, it's all good news, but fine. The really good news is, look here, we have an IK cubed. So just as in the two-body, just as in the S-wave case, the cut, now I can really do this, the cut associated with this propagator, putting those particles on shell, gives me IK cubed. It doesn't give me IK this time because there are 2 extra momenta in the loop. If I did this for D waves, I'd get IK to the 5th, and so on and so forth. So that's nice. That is a prediction of the theory, as Dr. Kaplan emphasized. That's because that's low energy physics. Those particles, if they're near their mass shell, that's an infrared effect, and that's captured in the effective field theory. Now, the more complicated news is that we have this additional piece, which actually represents the fact that this integral that we started with is, how divergent is it? Anyone want to take a stab? So this one, in 3 dimensions, this one was linearly divergent. So this one is cubically divergent. So what's happened here? What's happened here is we've thrown away when we did this, actually, we threw away the cubic divergence because we used dim reg with minimal subtraction, set it to 0. And then, but if you have a cubic divergence, you're also going to have a linear divergence times a p squared, or in this case, so that's what this is. PDS has captured for us the linear divergence times k squared. And we need to renormalize both of them. So you might have thought it was overkill for me to write down the dimer with both pieces, but in fact, in P waves, you need both pieces at leading order, because you need this piece to renormalize the cubic divergence, and you need this piece to renormalize the linear divergence. Which goes back to what I was saying over here. In P waves, both of these things occur at leading order. All right. So I'm going to stop there, and then after lunch, we'll come back and talk about the phenomenological consequences of this and how we power count in P waves and so forth. Okay? Any questions? I haven't really done anything with the dimer yet. I mean, how would I say? Actually, maybe I'll just make you all. I have to think about this during lunch. Like, you have all the ingredients you need to dress the dimer, right? You have the bare dimer propagator you have the self-energy. So I haven't finished the calculation, but you can already, I would claim you can already see what's going to happen. I'm going to put the self-energy in the denominator with this. And then, as I was just saying, right, the self-energy is divergent, and this renormalizes the thing we threw away. That's why we can throw it away. And this y renormalizes the k squared mu PDS. That's why I said it doesn't matter if you put the 3 halves there or not, because in the end it's going to change, just going to change your definition of y. Okay? So actually, like, you all could do that calculation. And then you could match, because this is the amplitude, right? So you could match to that amplitude and blah, 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 blah. So, all right, so we'll see. But like, that's what, so I'm going to just basically give the result after lunch. And then we'll talk about, okay, so we have this thing that has, you know, an A1, an R1, and a K cubed piece. And then what does that mean in terms of how we power count P wave scattering? Where do resonances occur? Blah, 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 blah. Okay? Other questions? This is the operator I'm very proud of. So the M operator, if it acts to the right, you get the mass of the field on the right. If it acts to the left, you get the mass of the field on the left. So if you're doing it with 2 equal mass fields, you don't need it. But if you're doing it with a core neutron pair, you need it. So maybe, like, I have to, every time I need to remember the formula for the relative momentum, I have to look it up, because I can never remember where all the factors go. But the relative momentum of a pair is M1P2 minus M2P1 over M1 plus M2. That's what I'm trying to do here. And this is the object that is Galilean invariant, right? In other words, as I change frames, if I consider, I can change the total momentum, and the relative momentum sort of by definition doesn't change. Ah, yes, okay, hang on. So this one should be going this way. Yeah, right, yep. How is it equal to what? Yeah, so I changed a bit here, right? So if what I was trying to say was if I start with this for equal mass fields, and then I generalize to unequal mass fields, yeah, then, yeah. So now Tuhin's going to have to cross his stuff out again, and his notes are going to have to be even messier, right? But if I start with equal mass fields, so we have been doing this, which is where all those nasty 1/8s come from, because this is actually twice the relative momentum, right? So I'm going to divide by 2, and then if I divide by 2, this is the relative momentum for equal mass particles. And if I want to generalize that to unequal mass particles, I have to do this. That is true, yes. It's a good comment. Thank you. Yep. Yeah. Sure. So if I did MS, so a useful trick is just to say that MS is PDS with mu equals 0. So then you get this. And then it depends how sophisticated you are, whether you notice that you need a second counter term. So you might say, oh, it's finite. I don't need any counter terms. You would, of course, be wrong, but it's very tempting to say that, right? So I used PDS because in PDS, it is manifest that you need 2 counter terms. Yes. They would miss this term, but as long as they realized that they had dropped the linear divergence proportional to the energy, they would know that they needed a counter term.
Is it possible? This is usual.
Yeah, I think so. So let me try that. So you look at this integral, you say it's cubically divergent. So yeah, I mean, I try to do this with my students regularly, right? So you say, okay, so if I used a cutoff, I'm not going to use a cutoff, but if I did use a cutoff, I would get like some number times lambda cubed, and then some other number times lambda times ME, and after that, I'll get the finite stuff, right? And then you say, oh, okay, so I'm going to need two counter terms. I'm going to need a counter term that's energy independent and a counter term that's energy dependent. And of course, here I'm exploiting the fact, oh, I slipped back into equal masses. I'm exploiting the fact that this integral is a function of E, right? And this goes back to a question that came all the way on the first day, is how do I know there are no odd powers of K? It's because the integral is a function of E equals K squared, right? So to riff a little bit, right? If I did this with Coulomb-Green's functions, which are a function of the inverse Bohr radius as well, then I would actually have an even more complicated divergence structure, because I could have like a lambda squared times inverse powers of the Bohr radius or something like that, yeah. Okay, yeah, and a log. I don't have a log here because I can't get, because of it's cubic linear, blah, blah, blah. Right, yeah. So yeah, so I would argue that, so this is why it's actually fine to use, it's like any powerful tool. It's fine to use it as long as you know what you're doing, but if you don't know what you're doing, you're going to hurt yourself, right? So, so it's fine to use MS as long as you know what counterterms you need and you make sure you have them. And then you just realize that if you use MS, then these parameters have already soaked up a divergence for you. Okay. So two-loop calculation for, I mean, I don't have, in this theory, there is no two-loop effect for the self-energy. Right, because, I mean, the only thing that can happen is that the dimer splits up and reforms. So when I solve the Dyson equation, I sum to all loops, right? But the self-energy itself is sort of closed at one loop. So here's the Lagrangian. So the only vertex for the dimer is this one. So how am I going to get two loops? But this is the self-energy. So the self-energy is by definition one dimer irreducible. Right? That's the self-energy is the, what is that? The one particle irreducible one-to-one amplitude. Right, so I claim there are no other one particle irreducible one-to-one loop diagrams in this theory. Exactly, that's my claim, yeah. Yeah. Yes, exactly right. So if I introduced, exactly right. So suppose I introduced perturbatively. So maybe I shouldn't have said in this theory at leading order, right? So if I introduced perturbatively some correction, which went like K squared P prime dot P, then I could have like, I could do something like that. That's correct, yes. Yeah, then I could. And then I guess if this really had extra momenta, then these loops would be even more divergent. And then the question would be whether it was self-renormalizing or whether I needed yet another counter term or so on and so forth. So I don't need the, well, because I only need two renormalizations at leading order. And I don't need to write down this one, because this one is generated by this, right? This is the Hubbard-Stratonovich thing again, right? Here I can't strictly do Hubbard-Stratonovich because of the kinetic term, but the argument still works, right? If I set the kinetic piece to 0, I would exactly generate this. This one? Or, I mean, this may be too sophisticated for me, right? So,
relativistic term, like a new.
Oh, you're saying that, yes, okay, because pi is a, right, okay, because you're saying because pi is a vector field that couples to the momentum. Yeah, yeah. So yes, right. But I mean, I can also, yeah. But I don't think there's really a gauge principle at work here, in particular because the couplings are not fixed by any symmetry, they're fit to data. But yeah, I hadn't thought of that before. Yeah. All right, lunchtime. Oh, not lunchtime. Sorry. Last ball before lunch. I'm not going to do this because it's already like, I'm already using more than my time. But if you, in the first paper I wrote on beryllium-11, we gauged this Lagrangian and then we computed like the electromagnetic radius of the P-wave state. Right, so yes, I mean, so it does have, you can give it an internal symmetry if you want to do photons, right? And so fun thing to do actually is to write down the Lagrangian with the S-wave state and the P-wave state and then compute E1 transitions between the S-wave state and the P-wave state, right? So you can, there are all sorts of things you can do with electromagnetic interactions once you have this, and if you're willing to gauge the, essentially do minimal substitution and write down the extra operators so you know at what order the corrections to minimal substitution come.